Good evening. It's lovely to be here in the quiet Irish surroundings of the pub, bringing physics to all of you guys. My name is Shane Bergin, and I'm a physicist, and I work just down the road in Trinity College. And tonight I thought that I would take you on a journey. I'm not going to talk about my regular research so much, but I wanted to talk about my discipline, about physics. So I'd like you all to close your eyes. It's amazing how many people that won't close their eyes. Come on, close your eyes. Nothing is going to happen. And now, if you will, try and imagine you're back in the 16th century. So that's quite a good bit back, right? So Trinity is still there. Don't worry. So I want you to think what life was like then. There was no light apart from candles or fire or indeed the sun. But there was no artificial light. Okay, that's a lot of light, but there was no artificial. Keep those eyes closed. There was a lot of light. People died really young. We didn't know much about electricity. There was a thing called lightning, but no one really had a clue what that was about. And nobody had really, in the European world, thought about science since Aristotle and the Greeks. It wasn't a very enlightened time. You can open your eyes again now. You're back in the 21st century. And a lot has changed since then. So around that time, there was the Renaissance, and we think of Renaissance as something to do with art, and we think of it as something to do with music, but there was also a revolution in the way we thought about the world, in particular, the way we thought about science. And the term scientist actually really dates from around then. When did people start to do scientific things? This is hotly debated, but it's argued that one could really put kind of the beginning, you could set the clock around this time. People like Copernicus, have you all heard of him? Yeah, you know, Copernicus called, "You're not the center of the universe," that old joke. And Copernicus dared to be extremely different. Now, he was so radically different. He said that the Earth is not at the center of the universe, rather it's heliocentric, or the sun is at the center of what he considered to be the universe. And he was heretical. He was made by the church to renounce his theory, and he was only allowed to kind of go back and go, "Yeah, I'm actually still a scientist, haha," on his deathbed when somebody handed him his famous book, which was called On the Revolutions of Heavenly Spheres. And he was one of the very first people to dare to think in a different way. And he was joined by people like Galileo, who through being really ingenious, stuck two pieces of glass in a tube, and for the first time was able to observe the heavens in a way that no one had done before. He looked and he saw the moons of Jupiter. Can you imagine what it must have been like for a person who had been brought up to believe that the Earth was at the center of the universe and that we were all created from two people called Adam and Eve, and everything was written in a book, and the book was literally gospel, and then he was daring to think something different. Absolutely amazing. And it didn't stop there. All of this, where did it come from, right? Well, the Renaissance happened arguably because a lot of people died in the Black Death, right? So there's a lot more, like people were daring to think differently. Materials was also a big factor. So we were now able to print books, right? So all of the ideas from Aristotle were now being read and disseminated amongst people who could read. Now, it wasn't a lot of people, but it was much better than just people going around pubs telling people things, right? So you're able to form your own opinions. And from there then came a guy called Francis Bacon. And Bacon decided, or he thought he was a philosopher, and he is said to be the... I realise I'm sitting, you're a philosopher, aren't you? No? Yeah, oh dear. So Bacon... Very deep. So Bacon, and correct me, Matthew, if I am wrong, he developed what's called the empirical system, right? So Bacon decided, you know what, maybe Aristotle and the gang weren't so exactly bang on in their method of deciding whether something was accurate in nature or not. Aristotle basically said we should always figure out what's natural in the world, and anything that deviates from that is said to be unnatural, but it's still an aberration and it's wrong, right? So the empiricists like Bacon said, no, what we should do is remove all of our prejudice and then form what they called a hypothesis, and then go and test that hypothesis, and from it you form theories. And those theories will stand up or fall based on something called an experiment. And that is the scientific process. Now, people like to call it the scientific method, and that drives me crazy because as an educator, a method basically means you can only do it one particular way, but a process is something that you can play with. And the scientific process has actually changed a little bit since that time. But it's fundamentally, you know, it's kind of similar. There's still this idea of having a notion, and that notion comes from your experience of the world and observables, so things that you just see. Why is the rainbow with 7 colours? Do you know why the rainbow has 7 colours? It actually doesn't. It's that, I can't remember who it was, but it was somebody decided it should have 7, and we're going to just say, we're going to put a line and say, right, 7 colours. It could have been 12, it could have been 11, it could have been, I don't know, you pick the number, it could have been that. But all these little random things have woven their way into our scientific culture, and we just blindly accept them. And that's fine because we're busy people and we live in a world where we can't go around just every 10 minutes questioning things, unless, of course, you work in the School of Physics. You laugh, but I often come into work and I could find one of my colleagues standing on the stairs just kind of staring. And yeah, says the philosopher. So I want to actually give you a little demonstration of what I mean here, right? So what have I got here? What can you see? Okay, it's definitely a liquid, yeah, sure, and it's in a, what's holding the liquid? A beaker. Okay, so a piece of glass, and can you describe anything else about that? Anything that's...
Clear liquid.
Clear liquid, yeah, great, okay. Anyone have anything extraordinary that they want to say about that?
It's not that hot.
It's not hot? Okay, great. How do you know? You're making an assumption. Ouch. You can see what my first year lectures are like. So I'm going to now pour some of this liquid into a glass. Now what can you see? Come on, Colleen. What can you see?
Ah, it's like a beaker.
Oh,
No?
Yes, there is a beaker in the beaker. But I want to do something else now, okay? Is the little beaker still in there?
it's invisible.
Is it there?
Yes.
Is it?
Yes. Yeah, he didn't remove it.
Well, I can't see it.
Thank you. We have a philosopher here, and you know that physics used to be called natural philosophy. The beaker is not in there, unless you can prove it. So how do you prove it? So what's that called? What's the process of emptying it called?
Experiment.
An experiment. So doing the experiment, you've got hypothesis because your previous experience, if there is a beaker in there, but until you do the experiment, it's not in there. That's mental, isn't it? So this kind of stuff blows my mind, right? Physicists think they know the world. They don't. We haven't a clue, right? What we do is we have a map of the world that we're busy building, right? So we can describe lots of parts of the world. It's like Google Maps, right? So if you think of Google Maps, you see the world, and then you start zooming in, right? And some parts of it are very, very detailed, and that's just like physics. We know a lot about the electron. We're mad about the electron. We can describe it absolutely perfectly, we think, right? What we don't know so much about is the nucleus. We can describe it somewhat. People at CERN are busy trying to figure out where matter comes from. What is matter? What is the stuff we are made of? Fundamental. Last night we heard a huge amount about dark energy and dark matter. Things in the universe that make up a massive amount of it that we haven't a clue where to even begin in describing it. We know how much is there, but we haven't a clue what it actually is. And so that's what physics is. It's not just a big mumbo-jumbo stuff there where we haven't a clue and we're joining all together. It's just that it's a map of the world. It is not the world's. And it's the best map we have. And it's based on this process, this scientific process of doing experiments. And these experiments lead us then to build theories. But going back to that 16th and now to the 17th century, there was an absolute explosion of thought. We think we live in a revolutionary time. I've just finished this amazing book, and it asked the question, what was the most, which century gave us the most change? And everyone thinks it's the 20th century. The book concludes it isn't, right? Because so much other stuff in different parts of our lives happened in previous centuries. A third of known humanity died in the 13th century, and society did not break down. That's incredible. We think if the internet stopped working, there'd be anarchy on the streets, right? But in the 16th and 17th century, people started to question things like religion for the first time. They questioned society. They started to question knowledge, which is what brings us to science. And so there was this explosion of thought and freedom. And I am glossing over the fact that in the medieval period, the Arab world and other cultures around the world were busy working on mathematics and other things, and that fed into the eventual industrial revolutions in the European world. But of course, being European, we think it's all about us. But so I'm not getting into all that. But let's talk about things that we're very familiar with, but didn't exist before the times of Francis Bacon. It's the idea of chemistry, right? I'm a physicist, so going to take the make out of the chemist. But it was once alchemy, which was all about how you turn things into gold, right? But the whole discipline arose from basically the father of chemistry was an Irish man called Boyle. Did most of his work, well, he did actually most of his work in Britain, but we claim all the writers, so let's claim him too. The science of optics and how we see, it was started with the Greeks, but exploded in this time. So a guy called Hooke, who was meant to be a real nasty guy, and him and Newton had a big back and forth. Newton was so pissed at Hooke that when Hooke died, Newton destroyed all of the portraits of Hooke, and there's only one that exists today, and I think Newton had something done to it so that he kind of looks like Richard III. So electricity, there's another one. So Michael Faraday made the discovery in London in, I think in the 18th, maybe into the 19th century, but he discovered amazing things about electricity, building batteries. He discovered that if you have a magnet and you put an electric wire next to it and move it, it can generate something called a current. You can make electrons flow. Everything in your digital world today is powered by that very, very simple principle. Mechanics, Newton. Newton's book, Principia, is said to be the end of the scientific revolution. You're like, what? What about all that quantum stuff and all that? No, that's known as the period of reflection, right? So since then, we have been reacting to the scientific revolution. And so the world ate it up back then. The Royal Society was founded in London as a place where people could come together to share ideas. And they came together to tell each other through letters and through presentations about the most exciting things they had discovered and they could imagine. And they weren't afraid to fail, and they weren't afraid to explore ideas with each other. And people really, really went for it. It was part of culture. Science was a cultural exploit, just as the music of the classical era and the great paintings and writing was seen in that same vein. It was something for the common good, because science advances humanity. But things changed, right? It continued along this drive to exploit science and scientific process for agricultural first and then industrial needs. And eventually science was kind of subsumed into the machine of war. And as an Irishman, I know all too well about the ultimate exploitation of that, where we started to split matter and take energy from that split matter to make what's called an atomic bomb, seen as perhaps one of the I suppose, very darkly, one of the greatest advances of the 20th century, to be able to control that, or to, well, somewhat control it, you might say. So science was driven by money, and it was driven by countries trying to get up on one another. And I guess the common man or the common woman started to fall out of love with science. And we've been working very, very hard in the 20th century to try and to change that. So in the 20th century, we've had some amazing advances in science. Nothing that can compare to the scientific revolution that came a couple of centuries before. But one thing that happened is, in our universities, all of these disciplines, so me being a physicist, and my friend Eva, who's a physicist, but we could very rarely talk to each other, even though we're both physicists, about the things we actually do. Because my level of expertise and Eva's, they're not very overlapped. And I could do that with most other physicists apart from the ones who work exactly what I work in. And that's ridiculous. So this siloization of disciplines, what do you think physics is, I would ask you? I would argue that most of you might say it's that, or it's a subject in the Leaving Cert, right? If I could burn it, I would. Actually, I should say, when my first years come in, I tell them, if you give me a definition from this book in your answers, I'm going to take marks away from you. But we'll get back to why that is in a moment. Anyway, I'm marking scripts at the moment, so you can see I'm angry about that. But so we are trying really hard, and we are succeeding, as Will said, in bringing people around and bringing ourselves as scientists around to see that there's more to it than just being in the lab on your own, working in a discipline that you and only a couple of other people can really truly understand, but that real advances come from the overlaps. They come from the chance conversations you have with somebody who works in a different field, but you're able to impart your expertise to them and them to you, and you start to think about the spaces in the middle. Right? And that's where new, exciting things could happen. And why? What's the point? If physics is just a book full of definitions and so-called like learned facts, and they're there and they're black and white and they're right or they're wrong, and you get it like 100% or nothing, then what's the big deal, right? Well, the American Association for the Advancement of Science have this amazing project. It's called Project 2061. They founded it when Halley's Comet last visited, which I think was 1986. I was very young. The goal of this project is brilliant, right? One of the goals is it's based around this fact that the life-enhancing potential of science, technology, engineering, and maths, all those things, cannot be realized by the public until they acquire scientific habits of mind. The key word I left out there was, or maybe I did say, the life-enhancing potential. The point of science, not the pint of science, is that there's something in it about the common good. We live now into our 80s or 90s. We are enabled by technology that can do amazing things. It's said so often, it's become cliche that the device in your pocket has more computational ability than the rockets that sent man to the moon for the first time, which was a huge advance. All of these things, all of the medicines that we have available, all of the facilities, the fact that you can travel from here to Australia within 24 hours, when at the beginning of the scientific revolution, it would have taken a week, I read, to go from Plymouth near Cornwall to London. A week. And you'd have to go and change horses. You could only do this if you were rich. So now, almost anyone in Ireland can travel amazing distances in a very short period of time. Why? Because of science, technology, engineering, and maths. And it's all of those things, and it's not one of them on their own, and it's not one person working in the lab on their own, but it's the entire team. It's the entire community that are building on this 300 or 400-year-old process. We have worked out a way to know our world, and we're exploiting it. And each of us scientists in labs and teaching, and any teacher here who is also a scientist or a doctor, who I dare sometimes say they're scientists too, they're pushing things forward as well in their own way. So that's great. So we keep churning out the so-called STEM graduates. Not a big fan of the term STEM, but we keep pushing them out, right? So therefore, things will change. We're going to sort it out, because we're going to have loads more graduates, and those graduates are going to go out into the world and spread the good news. And I often think, actually, when I give science talks and I get really into it, oh my God, he sounds a bit like a priest going on about things, but hopefully you can see the distinction. So I'm wearing a quality badge, and I have physics below it. So somebody asked me today, going, oh, is physics not equal? Yes, we can. So there's a whole lot of talk going on in Ireland at the moment about reforming our junior cycle, and particularly I'm interested in the reform that's looking at the junior cycle science programme. And we think this is really timely. We think this is of our era, it is our problem, it's something we're doing wrong or right at the moment, but it's about us. No, it's not. So since the 19th century, scientists and engineers have become increasingly concerned about the way we are teaching these subjects. So I want to read you something. This is like, it cannot be too soon or too often impressed upon the beginner that a mere acquaintance with the facts does not equate to a scientific education. Ironic. Knowledge is not the memory of fact, but comprehension of their meaning in the story of nature. And that was said in 1886 by a now long dead colleague of mine called Preston, who wrote some really interesting books about heat. And he was talking about our undergraduate students in Trinity. And arguably, things haven't changed. Our students come out knowing a lot of fact, but arguably, they don't get to know what physics is. And so, unless we can start to change that, then our students will come out and they'll be 6 or 7 years out of college not doing physics anymore, and you ask them to talk to you about your degree, and they just go, sure, yeah. So they don't hold on to it, right? And they're not thinking about, I can be creative in physics, I can be playful, I can be artistic, dare I say it, I can bring in all of these other skills and be proud and wear your badge that says I like physics. And so we really need to change that. And so my colleagues and I have started to make some changes in the way we actually teach our undergraduate physics program. So in the lab, the students would traditionally follow a recipe book to do experiments. And so we decided last year, let's throw the book out, right? See, and now you can understand why I don't like the books. I want the student to figure it out themselves. So I give them a challenge, say, determine little g, which is acceleration due to gravity, off you go, right? We're trusting you, you have 3 hours, we're here to help, but we're not going to tell you what to do. We'd just like you to be creative, use your imaginations. Imagine you're a physicist. Imagine I'm a Martian, the teacher, that's coming down to Earth and is going to have to understand this concept of gravity for the first time. What would you do? And you let them off. And you know what? They do absolutely amazing things. At the start of the year, they go, sir, they don't call me that, whatever, your man, how would you like us to be creative? What does that say? How would you like us to be creative? What way would you like me to do this? No, you to do it yourself. Yeah. But how do we get the marks? Right? You can see how it's so ingrained that education is all about the grade at the end, and it's so unfortunate when that's the case. But eventually you break through and you start to get them thinking in their own terms, not being held by this grade at the end, but rather thinking about the fact that they're learning to be a physicist and act like a physicist, and dare I say it, then become a physicist. And it's wonderful. And at the end of the year, we surveyed them all in a way that involved those students, so they helped us build the survey. Not us as teachers going, what was the learning outcome of your project? And we're like, what's the learning outcome? But rather we got them stuck in and was like, okay, help us measure whether this worked or not. We wanted to do an experiment. You know what one of the big things came out was? They said we had so much fun. And that's great because, as any physicist who you've heard here tonight or if you hear at the other nights, is the thing that should come through about these talks and about our discipline is that we genuinely love what we're doing. Whether it's in the lab or up at a lecture podium chatting with students. And that is at the heart of physics. It's getting that conversation going about a topic you love. And it doesn't just end with our undergraduates. So as well as you heard me say that American Association for Advancement of Science quote about the true potential of science only really becoming true for us all is when the public at large acquire scientific habits of mind. So in order to get stuck into that, I and my colleagues decided, let's talk to Dublin about physics, but crucially, let's get Dublin to talk back. So 2 years ago, we decided we'd put physics adverts on Dublin's DART train, and we called our project DART to Physics. And I dreamt it up when I was supposed to be correcting lab scripts, and I was just looking for, you know, when you're really busy and you just start cleaning your office and you think that's work too. And then you're like, I'll just do that, and I'll just do my expenses, and I'll just check this stuff over here, and I'll go talk to my friend about that very important meeting, and then you're like, yeah, I still haven't done the real work. So it was one of those days, and I entered this competition to think of a new way to bring science to people, and we dreamt up this project, DART to Physics, and the idea was to spark citywide conversation about physics by putting zappy adverts on the DART. And I've given you all one of them this evening, and it's called a Fermi problem, and this is a style problem that I would give with my first year engineering or physics students every year, and I'd ask them something like, how many leaves fall in Dublin every autumn? That's what you have in front of you, and the So I had a couple of, is this a trick question? Surely there isn't an answer. Is this something about leaves not actually being leaves was one that I got. Or somebody else was like, is the number 42 the answer? So again, we're all programmed to think, what way does he want it? Right? What way is he looking for it? If I gave that to 7 or 8 year olds, they'll have a go. And they really will have a go, right? You get these wonderful abstract ways of thinking about this problem. And that childlike way of imagining it, armed with one of these, my trusty calculator, which I better not lose, that's all you need. There's no equation. There's no law or log or anything like that that you need to refer to. You can do it with a calculator, some simple estimations about maybe the way I might do it was think, how big's Dublin, right? It's like a semicircle shape. What's the radius of the semicircle? Can you work out its area? What percentage of that area is covered in trees? How many leaves are on the average tree? And then you multiply. And when you do it, and I do it with 200 or 300 students every year, and I get all their answers, and I average them all, and I plot what's called a distribution of answers, you get this really neat distribution around the answer, or the figure, 10 billion. 10 billion. But, you know the best answer? Wow. There we go. Nobel Prize. Did she just write that down? That's amazing, right? But that's the second best answer I've ever gotten. I asked this in a school I went to visit over the last year, and one child very confidently put her hand up and said, excuse me, I have an answer. And I said, yes, what's your answer? She goes, roughly the same number as last year. And you know what? If that was in an exam and I'd asked it, she'd get 100%. It's bang on. Like that's so thinking like a physicist. That's great. So there were loads of these things that we had up around the city for a period of 2 months. And I did it with my colleague and friend Jessamine Fairfields and Evie Yehuda and Colette Murphy, both of whom were in Trinity with me. And we had great fun connecting with Dublin through these quirky statements like, is the person next to you on the dart standing too close? Don't worry, there may be empty space. So for the non-physicists, what that means is that most molecules are made up of empty space because all the matter, all the mass is in the centre, which occupies a tiny, tiny proportion of the volume. Or what about everyone on this dart is attracted to you? Gravitationally. Or everyone in this room is hot, thermodynamically. Or we told them things like the moon is escaping the Earth, which Eugene referred to earlier on, and actually is escaping. So they put that retroreflective mirror on the moon in 1960-something, 69, and ever since then, laser light has been bouncing back from the Earth to the moon, so we can't, within, I think, a couple of centimetres or maybe millimetres, say how close the moon is to us at any one time. And I can tell you shockingly that due to the rotation of the moon around the Earth and it dragging the tides with it, the moon is escaping the Earth at the rate of around 3 or 4 centimetres a year, meaning our days are actually getting longer, right, to the point at which the moon is just going to disappear and the days will be massively long. But don't worry, we'll be long dead from the growing sun at that point. Which brings me to another dart of physics point. And that is that we are all made from stardust. And I think this is an amazing place to end. Every element apart from hydrogen in your body, in this room, and absolutely everything around us has come from the death of an exploding star. So you're made from stardust. You are the stuff of stardust, and we know that because the scientific process has allowed us to figure that out and say it with certainty. And that's absolutely amazing. I think, why aren't there more poems and songs and things and pictures written and drawn and produced about that amazing fact? Why aren't people inspired by that? Why isn't that on the front of this stupid book? Well, I don't know, but it's a good question, I think. So I'm going to leave it there, and I'm going to finish by telling you that Dart of Physics is turning into City of Physics this year, where my colleagues and I will bring physics to canvases large and small around our city, trying, we hope, to get you guys to talk with us about physics. Because as an educator, I know when you listen, you take in a little, but you don't learn a lot. However, when you have a conversation about the topic, you learn so much more. And the ultimate goal is when you start to create your own stuff in response to what that conversation is. That's the ultimate goal in any communication or in any educational format, is that you actually start to create content and analyse that yourselves. And that's what we hope City of Physics will achieve this year. And I hope all of you will be part of it and take part in it. Many of you are physicists, and if you're interested, you can follow us on Twitter at Dart of Physics. Thank you very much.